welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright. So, in the previous module we have seen the Bayesian or Bayesian MMSE estimate for the parameter h given the observation y when h and y are both jointly Gaussian, alright, and h and y are 0 mean. So, now in this module let us consider the scenario where the means are non-zero, correct. So, previously we have seen the MMSE estimate. We have already seen the MMSE estimate, that is h hat equals expected value of h given y when these parameters h comma y are jointly Gaussian, correct, that is the first point, and also expected they are 0 mean, that is expected value of h equals 0, expected value of y equals 0, meaning that both of these are 0 mean, alright, with the parameter h and the random variable y, both of these are 0 mean. Okay. Now, let us now consider a scenario where these are non-zero mean. Let us now consider the non-zero mean scenario. Let us now consider the non-zero mean scenario. Okay. Let expected value of the parameter h be equal to mu h, okay, and also let expected value of the observation y be mu y. So, we are basically now considering non-zero mean, this is the non-zero mean random variables, alright. So, they have means which are not 0. Now, what we are going to do is define two new random variables h tilde, which is h minus mu h, and y tilde equals y minus mu y. So, from h we subtract its mean mu h, from y we subtract its mean mu y. Alright. Now, you can see h tilde and y tilde have 0 mean, alright. So, that naturally follows because expected value of h tilde equals expected value of h minus mu h, which is equal to expected value of h minus mu h, and this is equal to 0. Similarly, expected value of y tilde equal to 0. So, now given non-zero mean parameter h and observation y, we have converted them to 0 mean equivalents h tilde, 0 mean equivalent parameter h tilde, and 0 mean equivalent observation y tilde. Now, I know the estimate of h tilde given y tilde, alright. I am going to form that first, and from that derive the estimate of h given y, okay, and that is very simple, alright. So, now I need r h tilde which is expected value of h minus mu h whole square, which is nothing but the variance of the parameter h, correct. This is r h comma h. Okay. Similarly, r y tilde, this is the variance of y tilde, which is r y tilde square, expected value of y tilde square, which is expected value of y minus mu y square, which is equal to r y y. Other thing is we need the covariance, that is expected value of, that is r of h tilde comma y tilde, r of h tilde comma y tilde, which is equal to, this is the expected value of H tilde into Y tilde, okay, H tilde into Y tilde, which is equal to, which equals the expected value of H minus mu H into Y minus mu Y, which is equal to, which equals again the covariance, all right, of H comma Y, which is R H comma Y, R H comma Y, all right. Okay. Now, what we have, all right, now the estimate of H tilde given Y tilde, that is the estimate of this modified parameter H tilde given the observation Y tilde, we know this is given as, let us write this down, this is H tilde hat, the estimate of H tilde, this is your estimate of H tilde, this is equal to R, we already know the relation R H tilde Y tilde R Y tilde Y tilde inverse times Y tilde. Okay. So, this is your MMSE estimate of H tilde given Y tilde, all right. We have the same expression H tilde hat equals R H tilde Y tilde times R Y tilde inverse into Y tilde. Previously, we had H hat equals R H Y into R Y Y inverse into Y, all right. Now, what I am doing is in the same relation I am replacing H by H tilde and Y by Y tilde, okay. And now, you can see clearly, look at this, we have H tilde equals H minus mu H, this is a constant, this is a mean. Therefore, the estimate H tilde hat equals simply the estimate H hat minus mu H, correct, H hat minus mu H, or in other words, because mu H is simply a constant, all right. So, H tilde equals H minus mu H, which implies the estimate of H tilde, that is H tilde hat equals estimate of H, H hat. What is this H hat? H hat is estimate of H, estimate of the original parameter, all right. There is a simple relation, original parameter H. Estimate of original parameter H is H tilde hat is H hat minus mu H, which also implies, now if I have to write it this way, now rearranging this, this implies that H hat equals H tilde hat plus mu H, we have that simple relation, okay. Now, substituting this, we have H tilde hat equals H hat minus mu H, which is equal to R H tilde Y tilde R Y tilde inverse into Y tilde, but remember Y tilde, this is equal to Y minus mu Y, which implies now H hat equals, now look at this, R H tilde Y tilde is nothing but R H Y, this is nothing but R Y Y inverse, because R Y tilde is R Y Y, Y tilde is Y minus mu Y plus mu H, from the left I bring it to the right, I have mu H, and that is the expression for your MMSE estimate. That is your expression for the MMSE, that is your expression for the LMMSE estimate, that is your estimate expression for the what is this? This is the MMSE estimate of your non-zero mean parameter H non-zero mean parameter h given non-zero mean observation given a non-zero mean observation y. So, what we had previously, we considered the parameter h and y to be both Gaussian and also zero mean. Now, what we have done, we have relaxed the zero mean assumption and we said h and y are still jointly Gaussian. However, h has a non-zero mean mu h, y has a non-zero mean mu y, and in this scenario, what is the estimate of h given y? All right, and we have a simple expression. What it is basically simply subtract the mean mu y from y, compute the estimate, and then add the mean mu h separately, and that is what we have over here. If you look at this expression, this is simply r h y into r y y inverse into y minus mu h and then followed by addition. So, initially we are subtracting the mean mu y from y, computing the estimate and then separately adding the mean mu h. Okay. So, that is a very simple relation. Now, the variance, the MSE or the mean squared error, this will be, remember previously we had the expression r h h minus r h tilde y tilde. Wherever I had y, I am substituting y tilde, wherever I had h, I am substituting h tilde. Now, r h tilde, remember this is equal to r h h. So, this remains the same expression r h y r y y inverse r y h. So, this expression is valid again for the, this is the expression for the mean squared error. However, now remember r h h, r h y, these quantities are defined slightly differently. Remember r h h is not expected value of h square, but rather expected value of h minus mu h whole square. R h y is the covariance, that is expected value of h minus mu h into y minus mu, and similarly r y y equals expected value of, let me write this separately, r y y equals expected value of y minus mu y whole square. All right. So, just remember this change in definitions for the non-zero mean scenario. All right. So, let us do a simple example to understand this MMSE, to understand this MMSE estimation process better. All right. Let us do a simple example to understand this. Okay. So, let us consider a simple example for okay. We have two jointly Gaussian parameters, let us say h comma y are these are jointly Gaussian parameters. Okay. These are jointly Gaussian parameters with expected h is equal to 5, that is this is a non-zero mean, and expected the variance of h is expected h minus mu h. So, expected h is 5, which is basically your mu h, h minus mu h square expected value is nothing but the variance sigma h square, which is also r h h, this let us say is equal to 1. So, sigma h square equals 1, which means sigma h is also equal to 1. Okay. Now, consider expected y equals, let us say this is equal to 2, which is equal to mu of y, expected y minus mu y whole square equals, let us say this is equal to, which is basically your sigma y square, which is basically r y y, this is, let us say, this is equal to 4, sigma y square equals 4, which means sigma y equals 2. Now, let us say the correlation coefficient rho, which is basically your correlation coefficient of y comma h, which is equal to, let us say this is 0.8, which definition is basically, remember the definition of the correlation coefficient is expected value of, let me write it properly, this is basically nothing but expected value of y minus mu y, or this is a scalar scenario, h minus mu h times y minus mu y divided by sigma h into sigma y, which basically implies, now from this correlation coefficient, I can derive the covariance, and I can derive the covariance. Now, you can see this covariance is nothing but expected value of h minus mu h into y minus mu y. This is basically your r of h comma y. You can see this is nothing but rho y h times sigma h times sigma y, and what is this? This rho of y h, this is given as 0.8, sigma h square equals 1, which means sigma h equals 1, sigma y square equal to 2, which means sigma y equals 2. So, this is 0.8 into 2, this is 4 by 5 into 2, this is basically your let us put it this way, this is basically your 8 by 5, which is equal to this is equal to 8 by 5, which is basically 1.6. Okay. So, this is basically your RHY. So, RHY is basically 1.6 or basically 8 by 5. Okay. So, this is basically your 8 by 5. Okay. So, now we have RH. So, basically now the MMSE estimate, alright. So, now we have all the required quantities, and now I can compute the MMSE estimate of H given Y, alright, given that H and Y are jointly Gaussian, and we know the relation for that. That is basically your H hat equals RHY into RYY inverse into Y minus mu of Y plus mu of h. We know RHY, that is equal to 8 by 5 times RYY inverse. We know RYY, that is sigma y square equals 4. So, this is 1 by 4 y minus mu y, we know mu y, that is given as 2 plus mu h, that is given as 5. So, this is basically what this comes out to is, this is basically your 2 by 5 into y minus plus 5 minus 16 or rather minus 4 by 5, which is basically your 2 by 5 y plus 21 by 5. This is basically your MMSE estimate of the parameter h. This is basically your MMSE estimate of the parameter h, and remember we are also given the information. This is MMSE estimate given that, of course, this is assuming h comma y are, that is an important assumption. This is an important assumption that h comma y are jointly Gaussian. In fact, we will see later that even when h comma y are not jointly Gaussian, this is still an important estimate. This is known as the LMMSE estimate, that is the linear minimum mean squared error estimate. Alright, so this is also valid when h and y are not jointly Gaussian, except with a slight change of the framework, or with a slight change of basically the whole the estimation paradigm. Alright, but anyway, we will come to that later. Right now, given h and y are jointly Gaussian, non-zero mean, this is the optimal MMSE estimate of h given y. Okay, and this simple example clarifies this. Okay, so in today's example, what we have seen is basically we have computed the MMSE estimate, or the joint the MMSE estimate of h given y, when h and y are jointly Gaussian and not necessarily zero mean, that is basically non-zero mean. Now, let us also look at what happens when h comma y are vectors. Alright, so that will basically comprehensively consider the scenario when h comma y, these are vectors, and that is also very simple. It is a straightforward extension now, that is your observation, this is your parameter vector h bar, and this is your observation vector y bar. Okay. And now you can relatively easily extend this by observing the following thing. First, let us say that the mean of h bar equals mu h bar. The mean, of course, since they are vectors, the means of both the parameter h bar and the observation y bar are also going to be vectors. Okay. This is mean mu bar of y. Now, instead of the covariance, instead of the variances and the covariance, what we need are the covariance matrix, the covariance matrix of the observation y bar, covariance matrix of the parameter h bar, and also the cross covariance between these two vectors. That is what we need. Okay. So, what we need for estimation is again expected value of h bar minus mu h bar, or mu bar h into h bar minus mu bar h transpose. This is R H H. Since they are vectors, I cannot simply consider the variance anymore. This is the covariance matrix of H, or rather the parameter h bar. Alright. Similarly, expected value of y bar minus mu bar y times y bar minus mu bar y transpose. Okay. This is the covariance matrix of y. Now, the cross covariance can be defined as expected value of y bar, or cross covariance of h bar comma y bar, that is h bar minus mu bar h into y bar minus mu bar y transpose. This is equal to R h comma y. Okay. So, that is what we have. This is basically your cross covariance of h comma y. And now again, it goes without saying that we are assuming h bar and y bar. In this scenario, we are assuming h bar comma y bar are jointly, we are assuming that h bar comma y bar are jointly Gaussian. Now, in this scenario, the estimate, the vector estimate, now h hat, which is also the conditional mean of the parameter vector h bar given the observation vector y bar. This is given as, now instead of the small r h y and small r y, I am going to replace them by the capital, that is the instead of the variances and covariances, I am going to replace them by the cross covariance matrix and the covariance matrix respectively. Alright. So, that basically that is a relatively simple and straightforward extension of the scalar scenario to the vector scenario. Alright. So, now I have R h y r y y inverse times y bar minus mu bar y plus mu bar h, that is add the mean. Okay. So, now instead of the variances and the covariance I am using the cross covariance matrix, and this is the covariance matrix of y, R y y is the covariance matrix of y, alright. So, this is also another, this is another important aspect, and of course, the most general, this is the vector MMSE estimate. This is the vector MMSE estimate, and also the error covariance. Now we cannot, now we can talk about the, because we have a parameter vector, we have not simply the error, the mean squared error, rather the error covariance matrix, which is expected value of h hat minus h bar into h hat minus h bar transpose, and this is again, instead of the variances and the covariance, I am going to replace them by the covariance matrix, and the cross covariances I can replace, write this as R H H minus R H Y, replacing small r y y inverse by capital R y y inverse, that is covariance matrix of y inverse times R y h. So, this is your error covariance matrix. You can also call this as REE, which is basically equal to expected value of E bar times E bar transpose, where E bar is the estimation error. Okay. And that is it. That is basically your corresponding error covariance matrix for the vector scenario. This is the vector MMSE estimate. Remember, this is the vector MMSE estimate, this is the error covariance matrix for the vector scenario, right. So, we have the expressions for both of them, and we have derived them as extensions of their corresponding scalar counterparts, that is corresponding expressions from the scalar parameter and observation scenario. Okay. So, this basically comprehensively concludes this MMSE estimate when the parameter h and y are jointly Gaussian. So, what we did is we started with the scenario when h and y are Gaussian, but have 0 mean, extended it to a scenario when h and y are Gaussian, non-zero mean, also saw a simple example, and again later, that is in the last part, derived the comprehensive expression when h bar and y bar are now general, that is they need not be scalars, but vectors, alright. H bar is a vector, parameter vector, y bar is a observation vector, and h bar and y bar have non-zero means. The mean of h bar is mu y, mu bar y, mu bar h, mean of y bar is mu bar y, and now we have computed the vector MMSE, minimum mean squared error estimate, and also derived the error covariance matrix. Alright. So, using this, basically we are going to see how these can be applied in wireless communication scenario. That is something that we have to see yet, right. So, we are going to next see how this can be, this framework can be applied, for instance, in a wireless sensor network to compute the estimate of the parameter at the fusion center. Alright. We will stop here. Thank you.